All right. So we finished last week, started to talk about looking at some residuals. Okay, and remember that for ordinary least squares, we're calculating residuals as the discrepancy between our observed value of our outcome and whatever our model predicts that outcome should be based on our predictors. Okay, this is our residuals. And so the first thing we did is we pulled up this plot of residuals or standardized, or excuse me, our studentized residuals by our predicted values. So on the x-axis here, this is our predicted value of y. On our y-axis, that's going to be our residuals, right? And what we're looking at in this plot, we're looking at, again, looking for nonlinearity, right? We're wanting to see if there's any nonlinearity in our cloud of residuals. We want to make sure our residuals are linear. We want to make sure that our residuals are normal, right? And so what we would want to see is, and again, wanting to see residuals kind of bunching up around this zero line and then sort of spreading out equally in both ways, either way here. And then what we're wanting to do is make sure that our residuals are identically distributed. Okay, this is the homoscedasticity assumption of our residuals. We want to see basically the same kind of variation of residuals across this whole plot. Okay, now when we looked at this particular one, we see no real evidence of nonlinearity, so we don't have problems probably there. In terms of the normality of residuals, it doesn't look too bad. We've got maybe some points hanging down here, but Johnny, I think, brought up a nice little I'm thinking about, like, was it you, Johnny, that said if I could sort of put a point over there and it balances out, then it's probably not too bad, right? I think that's a good way to think about things and not something that I've heard before, but I think that's probably spot on, okay? And then homoscedasticity of our variable, of our residuals, right? Wanting, again, remember our rule of thumb is not wanting the spread at the lowest, at the least variable to the highest variable to be about a spread of about 3 to 1. Now here, remember, we've got kind of this weird line, right? We've got an edge on these. Anybody remember what that's due to in these data? What's that, Johnny?
You maxed
out the score, right? This is social support as our outcome. This is what we're predicting. In this student sample, pretty much everybody was reporting high levels of support. We had a negatively skewed variable because this is an artificial scale and it has a max value. What's happening is these are all people who reported max values. As we get closer, as our predicted value gets higher and higher and higher, this residual gets closer and closer and closer. We get what looks like an artificial shelf going on here, right? This isn't what we would hope to see, but again, starts to be a function of the types of weird stuff that can happen when your variables aren't normal and continuous. Okay, we're going to see this again in our next example that we walk through. Okay, so here all sort of instructions on how you can go through and do that in SPSS. Okay. And then the same thing in Stata. All right. So then we're going to go through and look at our residual plots, right? What we're looking for here is normality in our residuals. Now note that this is the plots that we're getting here. This is a marginal distribution. This is the distribution of the residuals as a whole, right? Technically, our assumption is based on the conditional distribution, right? Like at each level of my predicted value, I should have sort of the same distribution and a normal distribution of residuals. This plot isn't looking exactly at that, but if we saw a weird skew in these, we would definitely want to sort of look at something, sort of those would flag us as potentially problematic. We got an MPP plot, a normal probability plot here. Again, perfect normality is something that falls directly along that diagonal. We're a little bit off, but not too bad. Here's a histogram with a curve imposed on top of it. Not looking too bad, so we're thinking this is probably okay here. Okay. Then we're gonna go through and start looking at problematic values. Remember, we're looking at discrepancies. Discrepancies, these are residuals. We've already looked at our residuals in terms of their distribution. But what we're gonna look at now is pull those up again and think about looking at problems in terms of our predicted value. Do we have cases where our predicted value based on our model is very, very different than what we actually observed? Those are gonna maybe flag us as cases we want to investigate further. Leverages, remember, these are our multivariate outliers. These are gonna be the things that we're looking at in terms of X space. Y doesn't matter with this. Y has nothing to do with our leverages. It's all with our predictors. What we're looking at here is weird combinations, either individually or combination of variables that make a weird configuration of predictors that suggest that maybe we've got a case that is not super generalizable or particularly problematic. And then we have influence, which is going to be the combination of our discrepancy and our leverage. Okay. And we went through some examples here in terms of talking about kind of what some of this stuff looks like. Okay. Talked about our standardized or externally student standardized residuals. Remember that our externally student standardized residuals, these are residuals that is going to look at the predicted value of a given case if that case weren't in the model versus where that case is sort of now, right? And so if I've got a good model and that model is doing a good job of accounting for the case, the predicted value for that case, if it's not included in the model, should line up pretty well with the actual value we're seeing here. What this is doing is it's these residuals are specifically intended to avoid masking situations like this. Here in this case, that residual looks really small. The raw residual or the standardized residual is going to be really small, but actually this is really problematic because if that point wasn't in here, this is what our regression line would be, and we've actually got a large residual here, right? So what we're going to do is we're going to look at these studentized residuals, called different things depending on if we're in SPSS or if we're in Stata, but this is the idea behind this type of residual. There's lots of different types of residuals. This is the one we're going to work with mostly in our class.
Between like the discrepancy and the leverage, would you say there is one that is more problematic than the other, or are they like equally?
We're going to talk about that. Yeah.
Okay.
Yeah. Okay. So again, think about our studentized deleted residuals. These are going to be calculated as the difference between the observed value of Y for a given case relative to the expected value of Y in a model that doesn't have that variable or that particular observation in the model, right? And so again, what we're trying to do is pick up any weird masking stuff that may go on in our data. Okay. Again, our T residuals follow T distribution. Here's our general degrees of freedom, but again, if we're running regression models, hopefully we've got enough people in our sample where our T distribution is going to be asymptotically close or very close to a standard Z distribution. So we can generally talk about large studentized residuals anywhere from 2 to 4. All right. But again, remember taking this with a grain of salt. All of this is going to be relative. We're going to be looking at our data and saying, not just flagging everything that crosses a specific threshold, kind of taking this into context. Okay. So we've got box plots, histograms. Here we're seeing some low residuals. In this case, some stuff that's exceeding 4. So these are probably going to be things that we at least take note of, start to flag. What you're doing is you're keeping a log of usual suspects in this. You're keeping an idea, a look at, hey, these are the cases that keep coming up again and again and again. Those are the cases that are probably going to be the most likely to be problematic as you're working through this type of exercise. All right, so here, again, we've got in SPSS, we've got identified, picked out 3 of these that are exceeding or at least 3.5 and higher. So we're kind of getting sort of this set of cases down here. Remember that with these negative residuals, what this is saying is that my actual observed value of social support is a lot lower than what the model suggests it should be, right? And just so thinking about what these actually mean very literally to help you kind of understand what's happening with your data, okay? One of the best questions with applied data analysis, ask yourself, what does this literally mean? Like, what's actually going on? Too many times, I think we just look at these numbers and be like, oh, that's high or low. and don't think about what that actually means for our data set. If we actually think like literally, what does it mean if I have a studentized residual of -4? Well, it means that I've got a case that's reporting much, much lower levels of social support than what all of their predictor values would suggest. So maybe we want to go through, take a look and see what's happening in that case. Okay. And we talked about leverages. Okay. Again, remember that leverages, these are multivariate outliers. These are a weird combination of predictor variables. Okay. Y has nothing to do with it, right? Just only looking at your predictor values. Couple different types of leverages. Stata runs regular leverages, SPSS runs centered leverages. So the range and expected value of these are going to be average value. These are going to be a little bit different. Make sure whatever program you're using the appropriate benchmarks. Again, anything about 2 to 3 times the average value of a leverage is going to be something that starts to flag. Maybe I start to go through and think about. Okay. Again, remembering that with all of this, you're probably going to get a lot of cases just because real data is weird and doesn't behave well all the time. So wanting to go through, and this is why it's always critical to go through and plot your values, take a look and say, hey, what's going on? What are the cases that are probably going to be most problematic, right? Now, if I just look at this box plot, I'm like, oh, I start just identifying anything that's above 1.5 times your quartile range is problematic. Well, then I've got just a whole crap ton of stuff up here to deal with, right? If I'm actually looking at this, I'm like, well, we've got kind of a continuous sort of thing that are going out. We've got someone hanging case 276 is very clearly strange out here. We need to go through and figure things out. Now, again, so one of the most important, people will miss this and you're going to lose points for it. We don't just flag high leverage values. As soon as you flag a high leverage value, what you then need to do is go through and figure out what's making that case weird in X space. Like what about the combination of variables or individual variables is causing this to be problematic? So in this case, we've got centered leverages for 9 cases that are expected falling above 3 times the average value for leverages in this model. Right? That doesn't mean we're going to go through and investigate all of these, but it's going to say, hey, here's some cases that are starting to fall pretty high. Okay. Same thing in Stata. What we've done in this example, though, is started to pick out. We're going to use a little bit different procedure in our example to start to tease out why these leverages are popping up. But here, so these are standard leverages, not centered leverages. So we're getting a little bit different outcome here. We've got, in this case, a total of 5 observations with leverages that are exceeding 3 times the expected value, or excuse me, not the expected value, the average value of my leverages, right? And so here, just a little slick command in Stata that pulls up my highest leverage values, participant number, and then the values for all of my predictors here, right? And so what I can do is I can start to go through, compare that with my descriptives and start to see my highest leverage value in this case, leverage value 0.059. Okay, I'm for participant number 276. I've got an AAQ score of 16, which is a little bit low, not too bad. I've got a BASH reward of 11. That's pretty low, particularly with the standard deviation. That's several standard deviations below. So I've got a really low BASH score combined with a BIS score of 12, which is super low, right? And then an NOS score of 66. So I've got some weird combination that the model doesn't like it. It's saying that this is a weird combination. People typically don't have this configuration of scores. Having a really low reward score and a really low BIS score both together combined with an inordinately high, a little bit high. So there's something about this combination, right? Now, sometimes you can take a look at this, and if you know your variables and understand what they represent, you're like, imagine yourself, what does a person look like who has this configuration of scores? And if it doesn't comport to anything that you actually see clinically or in a experimental set, you're like, oh, this person has simultaneously super high self-esteem and also really high levels of neuroticism or something like that, and then super low goal orientation. Like, oh, I don't know what that looks like. That's kind of a weird kind of configuration, right? We're going to go through and hijack regression to give us a little better sense for what actual variables are likely driving those high leverage values. But this is what we always want to do. We identify them and then describe them, right? This is going to help our reader understand what's going on. It's going to help us understand, should this be someone who should be in the set? Is it someone who shouldn't be in the set? And sort of having a better understanding as opposed to just a data driven and just throwing out cases that sort of are not acting right. Okay. All right. So get us up to speed from last time. I just wanted to sort of bring us up because this is all probably mostly kind of new information to people. This, Jalen, gets to your point, right? We can have high leverages. We can have high discrepancy points that individually have the opportunity to exert impacts on our model that we would not like. But a large residual, a large leverage alone isn't necessarily enough to start sort of throwing our model around. So what we have here are measures of influence. Influence is the combination of both leverage and discrepancies. This is giving us a sense for how our model would change with the inclusion, without the inclusion of individual cases. Okay, so a couple of different metrics that we can think about. And again, you could spend an entire class just on regression diagnostics. There's an intense methodological literature and different variations on different metrics and things along these lines. Someone had mentioned a couple classes back, who had mentioned Mulholland-Obis distance. Okay, yeah, it's a variation. It's a transform of leverage, right? So at one point we were working more with Mulholland-Obis distances, but then I switched it over just because leverage is kind of a more standard thing. Patrick and they'll talk about Mulholland-Obis. It's basically the same thing. It's just sort of a little bit switched over. So and that's what a lot of this stuff is, right? So just want you to know what the specific metric is and how we go through and interpret it. Okay. Now for influence, a lot of different metrics. We're going to talk about Cook's D. Okay. This is a measure of the difference in coefficients for the full set versus coefficient that we would get with a target case. So similar to that externally studentized T residual, like what would things look like with this case in the model versus the case outside of the model? Okay, and so what we would get with a Cook's D, if I got a value that's greater than 4 times the number of people minus the number of predictor minus 1, it's kind of a threshold to say this might be something I might want to look farther into. Okay, we also have covariance ratio. Okay, this is an index to the extent to which an observation in our model starts to impact the width of our confidence bounds for our coefficients. Okay, so if I have this case in or I pull this case out, how does this change the confidence bounds of my coefficients? Hopefully it would change it nothing, because hopefully no single individual observation is going through and throwing things around a ton. Okay, now we can see covariation values greater than 1 improves the precision of estimation. Covariance co-ratio values less than 1 degrading the precision of our estimation, making our confidence bounds wider. Now I could go through and I could say, hey, well, why is this problematic? If I have covariance ratio greater than 1, it's improving my estimation. Why am I not jazzed about that, right? Well, problem is, if we go back through, look at this case, right? Here we've got a case that's a low discrepancy, low influence, but large leverage value, right? Like this is a case where there's weird in X space because it's way outside of what everything else is. And it doesn't impact our model all that much. Well, what it's going to do is it's going to dramatically underestimate the standard error of our model. With this point out there, we're just saying, hey, here's my regression line. And then if I choose a point that's way away from all the other ones, instead of way out on the end, it just tightens up that line a whole lot, right? And now all of a sudden my standard errors are going to be really small, probably smaller than they should be because of the case. This could be a situation where we'd see a covariance ratio that was a very sort of large value, more than positive, we would still want to go through and take a look and see what's going on. Yeah, it's decreasing the width of our, or it's increasing the precision of our estimate. But if it's just a weird case that just happens to fall on where my regression line would fall anyway, and it starts to drive down my standard error, I need to be concerned about that and check it out. Okay. So again, this in general calculated as a combination, influence is so a combination of my leverage and discrepancies. And again, same thing, we're just going to go through here, plot these out. Box plots are nice. Here we can start to see for my cooks, I've got 3 cases that are way out there, right? These are cases that I'm probably going to want to sort of flag and sort of think about, take a look at. Covariance ratio, this is giving us a little bit different metric. We're kind of seeing something else going on down here. So here we've got a total of 17 cases with cooks greater than 0.021. So for this model, that would be our threshold. This is going to change every time, right? Because you're going to have a different number of people, you're going to have different number of predictors. So these are not standard cut points. These are model specific, right? 25 cases with your covariance ratio. This is a lot of stuff, right? So again, wanting you to take these thresholds with a grain of salt and saying, hey, these are sort of cues that I might shine my spotlight on things, but grinding through 25 of these, there's probably some overlap in this, right? But that's going to get you too deep in the weeds. So what you want to be doing is, like, I would say very clearly, we've got 3 cases here that are suspect, right? And going to be associated with my highest values. Here, maybe this group of cases that I might want to take a look at, and just describing these as the cases with the highest values for these 2 metrics. Okay. Some different ways to represent this, just as examples in Stata and City, you can do these drop line plots, which are pretty cool. This is just sort of lining up all your observations and then the values, right? So here's just your ID number, and then on here is your cook. So just a different way to see, you can start seeing like, oh yeah, this is just a different way to represent it. It's kind of cool. Okay. Here we represent it as a histogram. Again, you can see those cases falling down there on your covariance ratio, right? So different ways of going through and looking at this would encourage you to use, like at this point, you know how to create box plots, you know how to create histograms and stuff like that. Different ways of visually representing stuff to try and make sure that you're capturing the gestalt of what's happening here. Okay. All right, questions about any of this? Okay, so some different things. Again, I told you we could spend an entire semester just on regression diagnostics. Some additional things that you will go through and maybe hear about going through and doing, Johnny, in your regression class. So these are maybe things that came up. Looking at linearity, if I have concerns with linearity, right, I can look at the scatter plot of my residuals versus my individual predictors, right? So I can go through and have SPSS give me predictors of my model, or excuse me, residuals for my model, and then look at the values of individual predictors. And I start to see weird nonlinearities that can indicate that something's potentially wrong. Other measures of influence, okay. DF beta, this is a metric that's used to look at the impact of the inclusion exclusion of a case, of a given case on coefficients for individual predictors. So before, when we were doing Cook's D, it was the impact on sort of everything. DF beta is looking at like the impact of inclusion exclusion on individual predictors, right? So it's a little bit more in depth. Procedures for looking through there. Looking at independence of your error. If you're worried about autocorrelation in your data set, right? Like, am I getting better? Is my model better at predicting cases that were collected later in my data or in my study as opposed to those at the beginning? You can do an index plot of my residuals. Just line those up. If I'm seeing a linear pattern where my residuals are getting bigger or smaller as the study goes on, that can suggest that there's something going wrong with my methodology. probably experimental or drift. Whoever's running the study might get looser and looser and looser, or I had bozos at the start and then got people coming in who were better, and then sort of things started to come down. Again, if I have concerns about things going on in my data, ways to tease that out. Some specification error. Does anybody remember what a specification error is, or where this came from? Yeah.
It's when like we don't have enough. We're essentially measuring the same thing.
Okay.
Twice, true.
Kind of, that can happen. It sounds like you're talking more about collinearity
Okay.
with this. Remember that one of our assumptions of our regression model is zero population error. And that our errors are uncorrelated with individual values for our X, right? A lot of this goes into making sure our models are properly specified. Properly specified model says that I've correctly identified the form of the relation. So if it's using a linear model, the actual form is linear and not non-linear. It's also saying that all the variables that should be in the model are in the model, and the variables that don't need to be in the model are not in the model, right? There's no way to test this exactly. A lot of this is coming in, you needing to know your literature, what should be in, what shouldn't be in, things along these lines, right? But there are ways of going through with added variable plots. What this is it's a statistical procedure to take a look at what happens if I add this predictor to the model versus this predictor to the model versus this predictor to the model, to start to take a more empirical approach to thinking about, like, should I have this variable in or out? Okay, now this is a practice. Again, so who's taking regression courses? Johnny, I know you have. Allison, you have. Gabe, you did. You had a regression course. Did you have a specific regression course? Okay, you'll see this. Anybody who's taken regression, did you do anything with added variable plots that you recall? Johnny, you're on doing a little bit of that. Yeah. Basically, it's something that's common in other areas. You don't see it too much in psychology, right? Because what this is basically any data set that we have is unique. And there's no reason to think that some unique feature of this data set should necessarily generalize to anything else out. So in our field, what you include in the model and what you don't have in the model should be a theory-based conceptual determination, not what sort of improves the model or doesn't improve the model. If theory says it should be in there, then you should probably put it in there absent some very clear evidence that it shouldn't be in there, right? So this is a more data-driven approach to model building that we don't see as much in our field, because our stuff is very much conceptually based, testing theoretical associations as opposed to trying to maximize my R-squared value. But it is a technique that's out there that you might see, and this is kind of what I'm doing. Last thing here that we will do that's pretty cool, pulled this out of some readings with Stata and stuff like that that I was doing, and then recreated over into SPSS, something we call combination plots. What we're doing is we're taking different components and putting them together in a common plot to start to identify weird cases, okay? So Stata has a leverages by squared residuals plot that you can just request, right? And what we've got down here on the bottom is your residual values, the square of your residual values, which makes them all positive. As you get higher values, you get larger residuals, meaning you're sort of farther and farther off on your prediction. Here, we're combining that against your leverage values, your multivariate outliers, right? And so what we're looking at here would be influential cases, some combination of a large standardized residual with a large leverage that would be hanging out sort of maybe around here, that would tell us, hey, we've maybe got a weird case, right, going on with stuff. Here, we don't find anything too bad, right? We're looking at this upper right quadrant. We've got some cases with large, so we've got 291. It's a large squared residual. So we're way off base in the prediction of this, but they're not weird next space, right? Here we've got a case that is weird next space, but I didn't do too bad in terms of where I'm predicting it, right? So what we're looking at is combination of the variables that are coming up as problematic. Okay. people kind of see what we're trying to achieve here, and really, this is looking pretty good for this set. What we would be looking at is sort of strange things over in this area. And it didn't come up, so we're gonna ride this. Okay. It's a different plot, what we're looking at here, and just utilizing, SPSS is not so good at this, but if you start using things like Stata or R or things along those lines, can start to code in different features. This is a really cool plot, in that we've got our leverage, now on the X value, on the X axis, our residuals on the Y. And what we've done is we've got individual case numbers here, but then the dot, the circle, the boundary is proportional to Cook's D. Okay, so here what we're looking at is big values with a combination of high leverages, high residuals, right? Either sort of in the positive or negative value with big bubbles indicating big D values, right? So here, 276 is actually looking not that great. We've got a large leverage, the highest leverage in our entire set, combined with a large studentized residuals and a really big Cook's D influence value. This person is someone who needs to be looked at and considered sort of what's happening with this. Okay. Yeah.
About 292. Do you agree with that?
292, not really, right? So there, again, for this one, what we're looking at is stuff up here and down here in these quadrants. Here we've got someone who does have, I mean, it's not the most influential case here, right? So you've got a large, well, it's large in terms of right? So you've got a large D value and you've got a really low residual, but your leverage isn't that bad. So you've got a case here that we're not doing a good job of predicting. And it looks like it's a reasonable influence value, but the leverage certainly isn't sort of where things could be, right? So again, but if we think about that case, and this one's kind of cool with this, I can't do that. I can't produce this plot in SPSS. But if I go through and I take a look at that same case right here in SPSS, it doesn't look as bad, right? Because you don't have that big old bubble around that for Cook's D, right? So you're saying like, oh, here, so here in SPSS, which is still a nice thing to do. Here I've got my centered leverages and my studentized residuals, and it's essentially producing the same plot. I just don't have sort of the proportional size of Cook's D in there. So missing a feature of things, but it's not the end of the world. It's still a good way to go through and take a look at stuff. So here we've got a version of the plot that just has your dots. The problem with this is that I can go through and just like sort through like, okay, what's my height? If I'm interested in figuring out what case that is, I can go through and say, okay, well, it's going to be whatever my highest leverage value is. I can sort through and go through and figure out by process of elimination what case that is, so I can go through and flag it. In SPSS, you can also attach labels to these. Okay, the thing is, and we'll show you how to do this. Note that these labels are not your participant numbers. This is just literally where this case is in your data set where you happen to have it sorted right now. Okay, so don't identify this as a ID number. This is just where this is sitting in your list of variables. If you sort it, all these are going to change around. Okay, so just know what you're looking at with this stuff. But a way to go through and flag so I don't have to comb through and continually sort my variables to try and figure out what this case is. Well, this is case in the position 335 in my current set. So I go through before I sort anything. I look, okay, 335, it's case. What is it going to be? 276. ID number 276. So, what's up?
Yeah, why would they do that?
Why would they do what?
Have it labeled by just like placing your list versus having some
It's
sort of.
it's just the way the interface is set up. Because and with any plot, you can do this and click on and you can hit labels and it'll just, you don't get a chance to say, hey, label this with this variable. It just will go through and label it as sort of what value it is or what order it is in the data set. Okay. There may be a way to go through and reproduce these in SPSS. I just haven't figured it out, and it would probably take a whole lot of time to go through it. The CAN package is just not set up to do this, you know, but we can work around still sort of stuff from, right? But a demonstration of some of the cool things that you can do, particularly in R, if you're an R user, you become an R user, there's just a ton of really cool stuff that you can go through and do. So, just, I don't know, I think it's really cool to go through and think about like, how do we look at our data graphically? We don't do this enough. Which I don't understand why we start to get hyper obsessed with sort of values when a picture would do a lot better job of just kind of telling us what's going on with the data. So if you can represent something visually, for sure do it. Right. So what I do, I'm going through and taking like, so in here I just kind of set up a little table in Excel to go through and say, okay, who are my frequent flyers? Who are my folks that just keep coming up again and again and again? And so here I've got case numbers that have come up. I've got my residuals, my leverages, my cooks, and my combination plot, right? And if I go through, probably 276 is the case I want to take the closest look at, and maybe think about like, is what's happening with this person? I might go through and compare the results of my model with and without that case. This came up as a high leverage, high influence value. On my combination plot, this is them sort of way hanging out there way on the end. So wanting to go through individually, none of this has to be problematic, but you want to sort of in sort of combination, looking at the potential impacts of these screening procedures. Questions? Yeah, Mandy.
I'm a little bit confused by how we're able to see like the number on the previous slide, like the one with the highest leverage.
Mhm.
And on the next page, it's asking us to represent the same thing, like on the bottom right. Is that supposed to represent the same?
Yeah, these are the same.
But the values are different, and that's okay.
Well, this is just attaching labels to all your points. It's the same plot.
Yeah, I'm saying with this plot versus
Yeah.
the one that's data.
Yeah.
Is that the same?
Yeah, it's
And the
not
values are fine?
exactly. Yeah, it's a little bit different in that we've got student residuals to leverages. Your leverage values. Your leverage values in SPSS, these are centered leverages, so it's going to be a little bit different. But yeah, so it's basically just a different representation sort of in the program that you're
I was just a little lost.
using. Okay, cool. Yeah, Kate.
Mine's more of like a big shred definitions of things. It's straight. So Cook's D is a metric of influence.
Yeah.
Influence is leverage and discrepancy.
Yeah.
And discrepancy and residuals are kind of like studentized residuals.
Yeah,
are
discrepancies and residuals are the same thing.
Okay.
Yeah, so our residuals are a measure of discrepancy. We can have discrepancy is sort of weirdness in Y space, like the difference between our observed and our predicted values. There are lots of different ways to go through and represent that, but they're all generally residual metrics. And so, yeah, that's just kind of.
There's a lot of different.
Yeah,
areas.
no, absolutely. And so knowing what goes with what starts to become important, starting to make conceptual sense of this. Okay. All right, last thing we're going to talk about here, multicollinearity. Okay, what we find is the unique contribution of a predictor starts to decrease as its correlations with other explanatories variables start to increase, right? We a few lectures back, we went through and drew those Venn diagrams talking about how I could have a predictor that has a very, very strong bivariate association with an outcome and contributes nothing to my model. Generally, that means that I've got too many predictors that are far too overlapping, right? When I have high collinearity in my data, what happens is my estimates, my regression coefficients start to become unreliable as a product of my standard error. My standard errors start to get very big, right? Remember that standard errors are the standard deviation of my sampling distribution. If I were to sample all possible samples of size 250 and run this model in all of those and then plot out my scores, well, I'd see if I have high collinearity, variability, the standard deviation of the distribution for that coefficient would be all over the place. which means for any given model, I don't know that my estimate of the actual population parameter is all that good. It just jumps around a whole lot, right? What we see is our coefficients start to become unstable and start to jump around with minor fluctuations in the data, right? So if I've got a high collinearity model, Gabe, and you go through back, oh, I don't like it, so I think this case is problematic, I go through, pull it out. Hopefully what happens is nothing much. But if I've got a high collinearity, the increase of the likelihood of my coefficients starting to jump around based on small tweaks starts to increase, right? Remember, our best case scenario with our generalized linear models are that principle of additivity, that every predictor I add to my model is contributing something unique, right? What happens in actual practice is a lot of times we add a lot of predictors, but all the predictors that we're adding are all accounting for the same variability in our outcome, and then we got a lot of collinearity. Everything's kind of stacked up on one another. Can't completely avoid it in psychology because everything's related to everything. And the vast majority of our measures are all self-report measures, and we got common method variance in everything. In clinical, we got negative affectivity and just general distress that sort of swamps everything. So we're not asking you to have orthogonal predictors, but what becomes problematic is just as you start to have lots of predictors that are basically measuring the same thing, even though you give them different names, it starts to become problematic. Okay. Now, with collinearity, the point estimates or coefficients remain unbiased. Right? They might jump around a lot, but the distribution, they're all centered around the population coefficient. So my parameter estimates or sort of my coefficients for my actual predictor aren't biased, but they become difficult to interpret because my standard error gets all thrown out of whack, right? Generally, my standard error is too big, right? So I might have something that's got what looks like a very strong coefficient, but my p-value is very large because my standard error is through the roof, just because I've got so much collinearity going on, right? So rule of thumb for my bivariate associations, if I've got predictors that correlate greater than 0.9, like, okay, but that's a really, really high threshold. If I'm measuring, I can't find two measures of the same damn construct that correlate 0.9 with one another. If you've got two variables that correlate 0.9, they're the same thing, right? So you'll see this as a rule of thumb, but there's other arguments that variance inflation factor of about 2 is problematic, right? Again, remember that our variance inflation factor, if we go through and we think about that as giving us a metric of the extent to which our standard errors are inflated, right? A VIF of 2, it gives me about a 40% increase in my corresponding standard errors, right? If I take square root of 2, I get that, right? 0.41. It's about a 40% increase in the variability of my standard errors that I would expect is if I had VIF of 1, no correlation in my predictors, right? So just thinking about using these metrics to give me a very literal idea of the impact that this is having on my standard errors, okay? So again, if you've got collinearity, very important, I would strongly recommend looking at your standard errors. We generally don't look at our standard errors. We've got a lot of covert multicollinearity. Definitely go through and take a look to see, do I've got stuff that's sort of weird and really large. So in SPSS, we can go through and ask for, remember, so here's our coefficients and our inference tests. Here's our confidence bounds. Here are my bivariate partial correlations. What we can add there on tack on the end is my collinearity diagnostics. This is giving me my tolerance values, my VIF values. Remember, tolerance values less than 0.1, VIF greater than 10 are going to be problematic, but that's problematic in that your model might start to give you fits and crash. You shouldn't be anywhere near any of this, right? And you should be able to see that in sort of an evaluation of your bivariate associations, but sometimes you got multicollinearity going on there, so it's not any individual predictor, it's a combination of predictors that come together. So sometimes, usually if you've got really high tolerance, really high VIF, you're gonna be able to see it because you've got predictors correlating 0.8, 0.9 with one another, right? But sometimes it can't. If you look at your bivariate correlations, none of them are looking like way out of whack or too problematic, right? And so what SPSS will also give you is this set of collinearity diagnostics. What this is looking at here, if you want to see which predictors are combining to cause you problems, this is a nice way to go through and do this. Now, this is a little bit difficult to interpret. You got to go through some rules, but if you're finding stuff up here where you've got something problematic, you want to go down to your collinearity diagnostics. What you're looking for in terms of problematic is eigenvalues that are close to zero. As you start to get down to the end of your predictors, you'll have the same number of dimensions as you have, what is it? Is it one more than the same number of as stuff in your model here, okay? So what you want to do, your eigenvalue, your last eigenvalue is probably always going to be pretty close to zero, right? But in combination with that, what you want when you look at your condition index, a condition index that's greater than 30, combined with the variance proportions greater than 0.5 on 2 or more variables, right? So it's kind of a special. What I'm looking for is a combination of eigenvalue close to zero, condition index greater than 30, plus variance proportions greater than 0.5 on 2 variables. Okay, so if I were to just go through and look at this, I would say, well, I've got an eigenvalue that's close to zero. I've got a condition index that's greater than 30. And then I got a variance proportion for fast reward at 0.66 and FOS total at 0.49. Boy, what's happening? Do I have a high correlation between these two variables? But if I go through and I look at, and those two variables probably are reasonably correlated, but if I go up and I look at my tolerance values, they're all acceptable. There's no reason for me to be down there kind of looking around with stuff here. So I don't have to worry about it. But if I am looking up here, see that I have problems with tolerance or my VIF, look at my correlation matrix, I'm not finding things that are looking like overly correlated or problematic or something that would flag. Collinearity diagnostics are a way to go down through and start to see, because what I might find is I have this, but then I've got, let's say, AAQ is 0.54, VAS reward is 0.66, and NOS total is 0.72. I'm like, oh, I've got some combination of AAQ, VAS reward, and NOS that's something about the combination of those variables overlap with one another to a great degree, right? Again, essentially what this is doing, and you probably see the same thing up here, is what we're doing is we're saying, let's say we take AAQ total and regress it all onto your other predictors. And if you've got, that gives you a really, really high multiple correlation, a really, really high R-squared value, suggests that the combination of these other predictors are almost perfectly predicting another one of your predictors, which is problematic. Okay, and so then we would need to start sort of teasing things apart. Yeah, Abby, what's going on?
I think you clarified my question.
Okay. Other questions about sort of looking at your collinearity stuff? Again, this is usually pretty straightforward unless you've got something where you've accidentally included subscales of a model in addition to a total scale, and then all of a sudden sort of things will start to pop up. It's really hard to crash a regression model, at least in OLS. You can do this pretty easy in an SEM, but still wanting for conceptual reasons, want to make sure that you know kind of what's going on with your analysis. Okay. And so this is just how you're pulling that out and data, same stuff, nothing different here. All right, so screening summary for your regression models. Lots more things to go through in multivariate modeling to keep an eye on. Accuracy, plausibility, missing values, univariate distributions. All of this stuff is stuff you've done before. So no sweat there. The only thing here that you need to remember is that with your univariate distributions, when we're doing our means-based analyses, our assumption was normality in my sampling distribution. Here, we're more focused on your observed distribution, because if your observed distribution is wacky, it's going to throw a lot of stuff off. Okay, and remember that for standard fixed effects regression, we technically don't have an assumption about the distribution of our predictors. It's that because we violate that fixed effects assumption and are running random variables in there. With that violation, now we need to make sure that our data are or our predictor or our data are multivariate normal. Otherwise, things start to go out the window. Okay. Univariate outliers or extreme values, that's fine. Linearity of bivariate relations, again, what we're looking at here, we need, in order to assume multivariate normality, we need to, what we need to have is a normal distribution of our variables. And we're assuming that all combinations of our variables are linear and homoscedastic. If they're not, then things start to become problematic. Also looking for possible specification error when we're looking at my bivariate associations. What specification error might I catch in an evaluation of my bivariate associations? What might I see in those scatter plots that might indicate an improper specified model if I'm just gonna jump forward with a linear regression?
You just need like a non-linear pattern.
Non-linear pattern, right? Maybe not, right? So maybe it's gonna be fine if I have another variable in the model that fixes it. That should really, if I've got something that's sort of doing this or strongly curved or something like that, I might say, boy, am I forcing is a square peg in a round hole, right? Am I forcing something into a linear model when it's actually not linear? Okay. Then we're going to look at our error distribution. This is going to go through, take a look at our residuals. Again, normally distributed and homoscedastic errors. We're also looking at nonlinearity and multivariate space, again, which would indicate a misspecification of our model. And then we're going to jump into our discrepancies, leverages, influences, going through seeing are there cases that are throwing us way out of whack. And then looking at multicollinearity in our data. Okay. So a lot of this stuff is things that you've done before and that you're going to be comfortable with. But then we're going to go through in this next example, go through some new stuff. Okay. All right. Questions before we jump into the actual SPSS piece of things?
Not at this moment.
Not at this moment. Okay. Thanks. You know what? I'm gonna declare victory, because I just went through and taught you that so good. There's just no questions, right? Everybody's just got it in their heads already. All right, so let's do this. Go through and pull up your handout, your multiple regression screening handout here. And then pull up your data set. So what we've got here is a set of data. Pretty simple model, right? What we've got is we've got individuals who come in for our clinic who have been involved in motor vehicle accident trauma. They've been in bad car accidents, having some difficulties. And what we're interested in looking at is what are the unique contributions of chronic pain, opiate use, and post-traumatic stress disorder on people's levels of function, okay? So we've got a PTSD as a continuous indicator, scores ranging from 0 to 136. Pain, a 0 to 6 scale that people have provided ratings on, level of accident-related pain. Opiate use, this is a dichotomous predictor, so to 0 to 1, right? Because remember that in our multiple regressions, our predictors can either be continuous or dichotomous. They're categorical, that's a no-no. But if they're dichotomous, coded 0, 1, that's fine. And then role functioning, okay? This is a continuous indicator, or we're reporting it as a continuous indicator of adaptive functioning, day-to-day roles, higher scores indicating greater levels of functioning, scoring from 0 to 100. Okay? And so our question is to what extent does pain, opiate use, and our PTSD score contribute to functioning in this group? Okay. So jumping into this, straightforward stuff, missing values, accuracy, plausibility, all the usual things that we've done in the past, right? So again, in SPSS, I can go through and sort pain, sort opiate use, sort PTSD, sort role functioning. Looks like I'm not missing anything there, right? So I'm feeling all right about this. So what I'm going to do is I'm going to go through and for my frequencies. I'm gonna look at opiate use because I know that's a dichotomous variable. Okay, so I'm gonna paste this. So I have my syntax file I can keep track of. Go through and run this. Not looking too bad. Zeros, ones, I got about a 50-50 split of people who are using opiates, people who are not using opiates. We're pretty good here, okay? No worries, remember again, can we have dichotomous variables that, or can we have outliers in the dichotomous variable? You have problems with dichotomous variables?
I'm 0, 1.
Remember, and so this is tricky. What happens if I have, what if I had only like 5% of the people in my sample use, using opiates? Yeah, then I've got outliers right there. I've got the imbalance of that is so big that I seriously have to question whether including this in my model makes any sense, right? That 5% of individuals who are using opiates have such a greater influence on my model than any one individual in the 90% who aren't. We can have, remember, go back through those screening slides and some of the basic stuff. We can have uneven splits in our dichotomous predictors can constitute extreme values, right? In that everybody's here except for the handful of people we have over here. And so then we have to think about like, what are we gonna do with this? Is this something that we can include? Because it can really start to throw off associations. It attenuates associations, weird stuff starts to happen. It gets not good, yeah.
At what point would we be concerned about an uneven split?
I mean, there's just some rules of thumb that talk about a 9 to 1. You know, it starts to become, it's not great, right? And this is the thing, this starts to get into is the design issue. If I'm gonna go through and I wanna look at something that's a low probability event, I need to do my best to go through and oversample it. Like you can't just like, hey, whoever comes in, and then we'll just sort it out on the back end. Because probably what's gonna happen is you're not gonna have enough people in your, not enough representation in your sample to reasonably look at what the thing is that you're trying to look at, right? So if that's something that you're building a study around and wanting to do, you need to have a plan for making sure you got representation of whatever target it is that you're looking for. Secondary data analysis, be like, oh, I'd really like to go through and take a look at this. Have to really consider, like, do I have enough people to make it worth looking at in this sample, right? So, I mean, if you go through and let's say, I want to look at like sex differences on some outcome, and I've got just typical of what we get, sort of an 80-20 split of women and men. Not great, but it's probably not terrible, particularly if you got a large sample. Right? You got enough there to kind of work with. You start to get more outside of that, and then things start to get tricky, right? Okay. But so keep that in mind. Yes, in fact, even though we can't have outliers or extreme values because my variable can only take on one of two values, it can still be problematic. I can still identify it as an outlier if the things are so thrown out of whack that I've got everybody but 3 people are over here in this other group. It really starts to decrease credibility of our model, okay? But here, almost perfect even split on opiate use, so we're doing okay there. We're gonna go analyze, descriptives. We're gonna look at pain severity, PTSD, role functioning, SAFE standard scores, skew, kurtosis. This is muscle movement for you all at this point in time. Go ahead and paste that. Go through, take a look. Let's get through this. All right. So any concerns with our descriptives here? What do you think, Jalen?
Role functioning has a really high kurtosis number.
Yeah.
I don't enjoy that.
What's maybe even more problematic than kurtosis? Or that role function variable?
Why is the standard deviation 25?
Well, yeah, we're gonna go through, so that's kind of a big standard deviation, maybe. What else is going on in that distribution in terms of indices that might flag your attention? Kurtosis is high, what else is high?
Would you say the skew is high?
Skew is high, right? Remember, like skew kurtosis greater than 2,
Okay,
right?
it's been a while.
Yeah, it's been a while.
It's a little rusty, okay.
But so again, with our observation, we got a reason, but for psychology, a good size sample, right? And so I'm maybe a little less concerned about the kurtosis as what that skew is going to start to do with sort of all the other screening stuff that I go through and want to take a look at. Okay, so but pain PTSD look to be okay-ish. So what I'm going to do, we'll just go through and do this because you already know how to do this stuff. Let's go through and take a look at our distribution. So what I've done here is I've just used my examine command, right, to go through and just ask for our plots like we've done before. All right, here's PTSD and pain. Danielle, any concerns with the distribution of these two variables?
The top one is, oh. Yeah, with the paint one, it looks really weird.
Pain looks really weird, right? But that's maybe more of a function of how SPSS is kind of binning things. Remember that's why the one weakness of our histograms is depending on how the program is binning things, it can start to change things. In terms of the overall distribution, is it looking problematic? Not really, right? We got a little bit of a negative skew there, but not too bad. PTSD total, that's about as good as things get in terms of what you're actually going to see. Got kind of a funky histogram. That's going to look different if, like, say, Johnny runs it in Stata. Looking at the box plot, right? That's the nice thing about our box plot. Box plots are the same no matter what, because there's just very specific rules about what those elements represent. Looks like maybe a little bit of negative skew sort of there on the bottom, but not anything that's going to throw us off too badly, right? So we're feeling okay about that. Then we go down through and we take a look at that role function variable that Jalen identified as sort of potentially problematic. Okay, Kate, what are we seeing with this? There are a number of things. What's happening with this variable?
Like bottomed out.
Yeah, I've got a floor on this, right? I've got a most of my samples lining up right at 0, right? Which indicates what? As in the measurement of this construct.
I don't really know exactly what 0 is, but a lot of people aren't.
Yeah, scroll back up.
Yeah, I'm doing that. They have lower functioning.
Yeah, we got
Really low.
Yeah, we've got people just bottoming out this scale, right? And so again, these are treatment-seeking individuals with chronic pain and accident-related PTSD. And so I'm not terribly surprised that people are bottoming out, but even though I understand why that's maybe happening, it's from a measurement standpoint, it's not great. What else is going on with the measurement of my outcome here? I said I have a 0 to 100 scale. Do I really have a 0 to 100 scale?
Like, it's not how it's presented there.
Yeah, how is it presented here?
20s.
Yeah. The range of my values is 0 to 100, but that's not actually what things are. Things are, I've got values of 0, 20, 40, 60, 80, 100, right? I've got a categorical variable. It's ordered categorical, but even though sort of I'm like, oh, it's continuous, it's actually not. I've got a level of measurement, right? I've got a categorical variable with go through and we go frequencies and go role functioning. right? I've actually only got 5 values here, right? I've got 0, 25, 50, 75, 100, right? So I've got 5 values, which generally we can say like, oh, we can kind of treat that as continuous. And we often do. But when we're actually looking at this, it starts to become evident that what we've got is a problematic outcome variable, right? It's not continuous in the true sense, it's ordered categorical. And it's not even well behaved, it's got a floor out because we got people just reporting like very, very low levels of functioning. And so it's not super discriminate down at the bottom end, everybody just gets chunked into this bottom value. And so we've got some problems with this. Okay, we've got high skew value, we've got problems with kurtosis. And so if I were to proceed with this, I can expect every other sort of screening thing that I do is going to be way off base because it's just the whole thing is going to be wrong. Okay, so what are our options? Yeah.
Like transform it.
Yeah, we can probably transform it, right? And that's probably the only thing we can do with this, right? There's nothing that's smooth here, right? Unless I just want to, I mean, the only thing you could do, and maybe this probably would be, this is one, using sort of a different model that counts for word like a zero inflated model that we're not going to get into, but something that specifically counts for stuff like this, or simply just chopping this in half, dichotomizing it and saying we've got people who are scoring at the floor and people who are scoring not at the floor, right? Problem with that is that we're just dichotomizing something that's very clearly a continuous outcome, but you know, basically our linear regression model is not well equipped to deal with this, right? And so what we would do if we are being responsible and thoughtful is we probably say we need to move over to a different model, probably an ordinal regression model with this. But if that's not our skill set, we don't know what to do with that. And so then we can go through and say, okay, what we're going to do is we're going to go try, maybe we can transform this and sort of make things look a little bit better. Okay. So what we're going to do is we're going to transform. What we're going to do is we're going to use a natural log transform. We'll talk about why this is advantageous, and if we have to transform, natural log is a pretty nice thing to do, right? Now, if we get into other areas of quantitative analysis, whole areas on transforms and box Cox transformations to try and sort of figure out what data specific transformation is going to do the best thing to sort of pull this in to make it sort of look okay. Problem is, again, if I'm just trying to predict an outcome and maximize by R squared, cool, whatever. But that's not what we're trying to do here. We're trying to go through and look at relations. And so I got a weird ass transform. It's going to make it even harder to go through and interpret stuff. Then I'm probably not feeling good about this. There are interpretive properties that are very convenient for natural log transforms. So that's what we're going to give this a shot to just try and see, does this sort of fix things? If it doesn't, then we're going to go on to maybe square root transforms, inverse transforms, things along those lines. But generally, wanted to go through and try and give a natural log a shot, right? So what we're going to do is we're going to go up to analyze, or nope, transform. And then we're going to hit compute variable, okay? And what I'm going to do is I'm going to create a variable. I'm going to just call it ln roll, okay? And then what I'm going to do is I'm going to go through and I am going to, in my functions, I'm going to click on arithmetic. And then I'm going to go down through and take a look at here until I find my ln. That's my natural log. So I'm going to click that. And so SPSS says, all right, what do you want to take the natural log of what? To take the natural log of roll functioning. And I'm going to hit paste. So here's my command right here. I'm going to go through, I'm going to take my natural log of roll functioning. And it gave me a bunch of errors or warnings, okay? What's going on with, I didn't calculate for a whole bunch of them. Most of
Zero
it.
values.
Yeah, I got a zero value, right? Zero is the low value of my row function. See, I can't take the natural log of zero. It's like dividing by zero, right? So what do I do, Kate, to correct this? Or someone else said,
Add one.
Add one
yeah,
to
add
everything.
one,
Yeah.
right? We just go through and add one. Because the scale doesn't matter anymore because we're jacking it around, so who cares, right? You can add 65.7 of it if you want to, but there's no reason to get crazy with it. So what we're gonna do is we're gonna go through and instead in my syntax file, I'm gonna set row functioning +1. Okay, gonna rerun that. Awesome. Now we've got everything looking good. And so what I'm gonna do now is I'm gonna go back to my syntax file. I'm gonna copy that. And then I'm just gonna look at this just for ln roll, because everything else looks good. I don't have to worry about other stuff. Go through and run this. If I do that. Here's what I get. If I go through and I take a look at my descriptives for this, just use the sheet because it's easier to see. What did, Abby, what did taking the natural log of my row functioning do in terms of skew and kurtosis?
It made them more reasonable.
It made it more reasonable, right? I've still got a skew of 1.6. That's not perfect, but it's better than over 2. Kurtosis went from 4 to 0.24. Jalen, do you like that? You were upset with 4 previously.
Oh,
You
yeah,
like
that
0.24?
makes me feel better.
Okay, Jalen feels better about current skew kurtosis value. So just looking at my descriptives, I'm like, sweet. I think we maybe sort of have something better, right? Well, if then we then go down through and examine our box plot and our look at our plot of our variable, how do we feel now?
Still grow.
Yeah, not much better.
Still grows, right? But now here's what we need to do, okay? We need to think about, we've still got weirdness. Now we've got the first quartile, the median, and the third quartile is all 0. Everything else is way above there, right? The whole thing looks like still a big mess, right? Is there a transform that will make this data look nice?
Not really, but you could dichotomize it.
You could dichotomize it, and that would maybe
But
be a better way to go through if we're willing to conceptualize our outcome as 0 or something that's non-zero, right? Thing to remember is what we're doing mathematically is we're applying a nonlinear transform to a set of 5 scores. Am I ever going to get more than 5 values in this set? It's always going to be 5 values. Those 5 values will differ, right? And we can go through and start to bring things in or out and sort of change things around a little bit. But are these graphs ever going to look nice? Not with these data. Now, if I've got sort of an actual continuous variable that does have skew, we can start to bring things in and things can actually start to look better. But here we've got ordered categorical data. We've only got 5 values. No matter what we do, as long as we're not just adding random variables to scores, it's always going to be 5 values. There's only so much we can do with 5 values. So looking at this I do not like. I'm not super excited about it. But my options to try through and cycle through different transformations means I'm gonna have something that might incrementally change so my skew and kurtosis value or my skew value a little bit, but it's not gonna make it good. It's not gonna make it normal. It's not gonna fix it, right? Here, at least with a natural log, I have something that's interpretable. And so I'm just gonna say, all right, if we're gonna do a multiple regression, we'll just kind of leave this alone where it's at.
So we only transform a log in terms of like if our skewness and kurtosis is, you know, out of that
range like quite a bit. We're not doing it necessarily for the fact that, because I know we were talking about how the scale's on a 0 to 100.
Yeah.
And it's making it like categorical, like it did it by the 20s or whatever.
Yeah.
So we're not necessarily doing the transform log because of that, we're doing it because of skew and syncretosis.
Yeah,
correct?
yeah.
Okay.
The skew is just really bad.
Okay.
Cause it was like 2 something, right? And we're just trying to get it incrementally better than what is, like essentially what we've got the wrong tool for the job with the linear regression, right? And we're gonna see that this continues to screw with us as we move through these different screening procedures. But if this is the tool we have, right, if my advisor says, nope, I'm just gonna run a regression model, then you're like, all right, well, let's try and fix it, make it as good as we can get it then in terms of stuff, okay? All right, yeah.
Last thing, because I know some people do instead of natural log, they do log base 10. Is there a difference?
What's that?
When you're transforming, instead of using natural log, you use base 10.
Yeah, you
So
can use a base 10. The thing is, and we'll talk about this, if I were to use a base 10 transformation on this, the shape would not look any different. It would be identical. It's just with a natural log, it sort of contributes, and we'll get into this, interpretive properties that are nice. And so base C is generally what would be recommended if you're gonna utilize this. Yeah, the actual base that you use isn't gonna change your skew and kurtosis values along that much or at all. They'll be identical. It's just going through and using doing that because there are certain ways where we can interpret the natural log that make this nice. Okay. Cool. All right, let's stop there. Go through, take 10, come back at 3:40 and we'll get started.
No, I never answered, so.
Fix it again. You know,
No, you're fine.
I'm gonna get a card.
All right, folks. Gonna jump back in, so we're working through, so again, all this stuff, pretty straightforward stuff that you already done with screening. The only thing we're doing a little bit different is playing around with some transforms, trying to get the idea sort of with this stuff. Okay. Okay. So what we're gonna do now with our transform variable, we're like, all right, this is as good as it gets. And so what we're gonna do here is just go through and do our standard looking at our descriptives, our z-scores for our pain severity variable, our PTSD variable, and then our new natural log of our role functioning. Okay. So here looking at our minimum and maximum values, have some values that are sitting about 3 standard deviations above below the mean. But with a sample size of about 200, is there anything we're too concerned about this? Probably not. And here, some confusion about like what to flag in terms of extreme value. Really with this, there's probably not anything to worry too much or even worth reporting with this. I mean, if you got a smaller sample, maybe, but this is all kind of within sort of bounds of what we would expect. And so there's probably not anything really worth noting here. Our role functioning variable is wacky. Well, we'll have already talked about that, right? So really not too much to address here. Yeah, Matt.
Did you record?
Yeah, I hit record. Thank you. Yeah, Jalen.
What if it's something crazy, like what, like 4, like 5?
Yeah,
What
then
is,
we
like,
would
the
go
okay?
through and say, yeah, there's something that's there. Or, and again, so we're using sort of the combination of information here. If I go through and I take a look at my values for my other stuff, I mean, I would say really PTSD is looking good. I've got 1, the histogram's approximately normal, right? Box plot's symmetrical. I've got 1 value that's 1.5 times the interquartile range above. Some negative skew with my pain severity scale, with the cluster of values sitting 1.5 times the interquartile range below on my box plot, but nothing really worth nothing that's really noteworthy there. It's really just that role functioning variable that we gotta figure out what to do with. But once we go through, execute the transform, take a look at our z-scores, there's really nothing much going on in there, so we're pretty good on that front. Okay. So now what we need to do is we need to go through, and what we wanna do is take a look at our bivariate associations, okay? Now, in this case, we've got three predictors and an outcome, right? So there's not too much to go through new, but as my models start to get bigger and bigger, I have more predictors. Then all of a sudden it starts to get a little bit less manageable. So what we're gonna do is to kind of simplify things. I'm gonna go to graphs, I'm gonna do a chart builder. It's gonna say, okay, so. And what I'm gonna do is I'm gonna go down and I'm gonna choose scatter dot plot. And I'm gonna go to this little matrix here. I'm gonna drag that up. Okay. And then what I'm gonna do is I'm gonna take all my variables. I'm gonna take pain severity, PTSD score, and my natural log of my role functioning, and drop down that, right? I've got opiate use. Opiate use is a dichotomous variable. You could put that in there, but it doesn't give you much of a scatter plot. You can start to see sort of problems with homogeneity of variance, which is actually, so let's go through and actually, let me go through and reset. Okay, let's do that. It'll be different than what we have in the example, but we'll just do it so we can kind of go through and take a look. So I got pain severity, opiate use, PTSD, and role functioning in here. So we'll just put them all in there. Okay. I'm gonna go ahead and hit paste. So the plot here is, command is massive, but go through and run it. Okay. Which gives us our graph. All right. Now this is fine, but it's a little cartoonish and it's hard for me to kind of see what's happening. So I'm going to go through and I'm going to start to do some stuff to fix that, make it better. So I'm going to go through and I'm going to double click on that and it's going to bring that up. So I'm just going to go to like an individual dot here and double click there. And it's going to bring up an option for me to go through and change. I'm going to turn those dots really small. I'm going to fill them up to something red so it's kind of easy to see. And I'm going to hit apply. Okay. So now what that's done is it's gone through and changed those dots, those little points, to something that's a little bit more manageable. Okay. And then what I'm going to go to do, I'm going to go to elements. I'm going to click fit line and total. If I do that, what it's going to do is it's going to give me a little regression line for everything, which is kind of nice. Okay. And then just as a reminder, I'm going to go to options. And I'm going to say show charts on the diagonal. Do that. And it's going to go through and plop in my histograms across these, right? And then the last thing, it's kind of small. I'm I double click on sort of an area of the chart and go to hit chart size. And I'm just going to say 600. Oops. Punch 600 in there to apply. Okay, so that's good enough. So it just made that a little bit bigger so I can go through and start to kind of take a look at things. Okay. So what I've got here is all of the bivariate relations between all of my variables here, right? To go through and take a look. Now, anything that has to do with opiate use here. Now, here the lower diagonal, the upper diagonal are functioning the same thing. It just flops it, so you don't have to worry too much about that. It's just sometimes there's things are easier to see one way than the other, right? So anything that's got my opiate use in there, there's not much of a scatter plot, but what we can start to do, go through and take a look at, to see whether we have a problem with homoscedasticity, right? So if I were to go through and say, for opiate use and PTSD, if for people with no opiate use, I had a huge spread, people with opiate use, I had a tiny spread, that would suggest problems with, what we would normally call last semester homogeneity variance. Same thing, same principle, we call it heteroscedasticity. So this is one reason why it can be nice to throw your dichotomous predictors in there just to kind of take a look. Now, if you got dichotomous by dichotomous, then that sort of starts to get not so terribly useful. But gave anything in there that would suggest problems with heteroscedasticity in the relation with opiate use?
Not really sure.
Not really, right? So I mean, again, if this was all this and then everything around here was clustered up there, then that would be like, oh, whoops, there's something weird going on. But nothing here going on, right? So as we're going through and taking a look, is there any concern in these data with possible issues of nonlinearity or heteroscedasticity, at least based on what we're seeing here? And Lindsay, do you see anything that is looking maybe problematic?
I'm not sure.
Anybody help her? Does it look fine? John, you think it looks fine?
I think so.
Yeah, I think it looks fine too. Right? There's not much here to be worried about. Is there anything here that looks obviously nonlinear? No, nothing that looks obviously nonlinear. The only thing that I might take a look at is sort of see if my role functioning and my pain severity. I could maybe imagine this as sort of being less variable on the high end than at the low end, right? Because we kind of got, again, with that heteroscedasticity thing, like we're looking at band shapes and stuff like that. So if I wanted to, I could go through, so we've got role functioning on the X and pain severity on the Y. I could go to graphs, I could go to chart builder. If I wanted to look at just that one, that relation, I could go through and I could say, all right, I want role functioning on my X and pain severity on my Y. So again, it looks like things are somewhat less variable, maybe at the high end, but not much. Anybody remember what our kind of general rule of thumb was as flagging problematic levels of heteroscedasticity? Talking about a 3-to-1 spread at the lowest versus the highest. We're nowhere near 3-to-1. I mean, it's lower here. I mean, we're getting a little bit of a fan, but it's not something that's going to be problematic for us, right? So again, if I take this distance and multiply it by 3, we're not there. So we're doing okay. Okay. So going through based on our scatter plots, looks like we don't have any concerns in terms of nonlinearity in terms of our bivariate relations, and nothing that's looking obviously heteroscedastic with this. So feeling okay about it. Kind of get what we're looking at with this. All right. So next thing we want to do here. Oops. Looking okay. Now what we want to do is start jumping into our regression stuff. Okay. What we want to do is go through and actually run our model and get our regression coefficients and our residuals so that we can go through and start to take a look at what that structure is looking like. So what I'm going to do is I'm going to go through back to my data. I'm going to go to analyze regression. I'm going to go linear. outcome is gonna be my role functioning variable. My predictors here are going to be. I'm just making sure I got the same order as in the handout. So I've got opiate use that we'll put in first, pain severity, and then PTSD. The order doesn't matter. I'm just trying to make things line up with what we got there. Okay. Then I'm gonna go to statistics. I'm gonna ask for confidence intervals around my regression coefficients. I'm gonna ask for descriptives. I'm gonna ask for part and partial correlations. I'm gonna ask for collinearity diagnostics. And then I'm gonna ask for case-wise diagnostics, right? What this is gonna do is it's gonna automatically go through and flag some stuff that are sort of exceeding 3 standard deviations in terms of some outliers and things along those lines. So we can go through and you could change this to whatever you want. We'll just leave it there. Okay. I'm gonna hit continue. I'm gonna go to plots. I'm gonna ask for my Z predicted and my X by my standardized residuals. Well, I remember these are in SPSS. This is gonna be your studentized related residuals. And so then we're gonna ask for histograms and our normal probability plots. Okay. You hit continue. And now what we're gonna do is we're gonna hit save, okay? And what we're gonna tell stated to do, or excuse me, SPSS to do, is I'm gonna ask for it to go through and it's gonna create variables. It's gonna save my values for my studentized deleted residuals for each case. So it's gonna give me my residual for each case. I'm gonna ask it to save cooks. And I'm gonna ask it to save my leverage values. And here you can see like all some of the other stuff that we had talked about, different types of residuals, predicted values, things like that, lots of different options. We're not gonna worry about that. We're just gonna focus on this stuff here. Okay. I'm gonna hit continue. And I'm gonna hit paste. So here is my regression model. You go through, run the whole thing. And I'm gonna get a whole lot of stuff. I'm gonna ignore most of this for right now. Okay. And focus first on this model right here. Okay. So again, if I go through and I double click on this and I go to options and I ask for y-axis reference and I click that, it's going to automatically put a line at 0 because that's what my residual should be centered around, 0, right? And then if I go through and I go to elements, I hit fit line, no, not fit line total. Interpolation line. I think this will give me my lowest. No, damn it. Undo. Can I do that? Yeah, no.
There's a little undo thing
It's a reset thing.
in the
on your
tool set,
file.
What's that now?
on the tool set bar.
Oh, nice. There we go.
And-
All right. Go options. All right. Y reference line. There we go. And then elements and say fit line at total. And what I'm going to ask for is instead of a linear, I'm going to ask for a lowest line. Remember that lowest line is just that one that kind of goes through and adjusts. Then I'm going to hit apply. All right. And then if I want to chart size. Blow this up to like 600. So do we like this plot?
It's the lowest line, like.
Well, so what the lowest is, it's just following and sort of making the best fit. So here we've got to get an edge, right? Because we got that low level, right? And so we're getting there, but then it's trying to account for this data. There's just so much stuff going on here. And then it's just kind of jumping up to go through and see there. Okay. So this lowest line is not linear. Am I seeing clear nonlinearity in these data? No, there's nothing really I've got a weird kind of, everything's kind of funneling down in sort of these patterns, but again, we've only got 5 different values in this, right? If we look at with these residuals, I've got 1, 2, 3, 4, 5 different lines. This is just a straight function of my weird ass outcome variable. It's making all my stuff look ugly. And that's just what's gonna happen because we're applying the wrong model to the wrong data. Yeah,
What if your line, like that straight line is not on 0?
it will by definition be on 0.
Oh, it's not. It's, I'm looking at it.
Like 0.6.
It's not.
Okay. Don't worry about that for right now.
Okay.
You've got maybe a different, you might have hit the wrong thing there. So don't worry about that. By definition, with OLS, it has to be 0 because that's just a property of the estimator. I just dropped, and it's not that important. I just dropped that in there just so you can see kind of a thick line, kind of where this should be at. Okay. So remember that when I'm looking at this plot, what I'm looking for is normality, linearity, and heteroscedasticity. Okay. What are my concerns? Do you have concerns with linearity? No, not really, right? I mean, this is doing something crazy and funky, but that's just kind of an artifact of what's happening. Are my residuals normally distributed? Not really. My conditional distribution all is, I mean, maybe down here, but I've got a skewed distribution in my residuals, right? So if I look for any given predictive value, right? So predictive value of 0, I've got everything stacked up here and everything else kind of coming up here. And I mean, I could put a plot down there, but I would need to, like, it's just everything's kind of going the wrong direction, right? So here I would say, like, I can't say that I have at least within my residuals that my residuals are normally distributed, at least the conditional distribution of these. Yeah.
So if there was kind of like a line of like other scattered ones below, we would be less concerned?
Can be less concerned.
Okay.
Yeah. But again, if you look at sort of, and this is why it's always important to think about, like, what am I seeing in these residuals that's characteristic of my data? I've got predicted values that are falling on sort of 5 tiers, same as I had sort of with my actual outcome, right? And so I don't have, and I've got a fair amount of, it's not like, oh, this is just on the extreme where I have a couple, but I have sort of, I've got problems with the distribution. I've got problems with normality here, right? Now, would we see that do we have a problem with variability? Are these residuals heteroscedastic? Not really, right? I mean, we've got some stuff there where there's actually 0 variability and some stuff here, but for the most part, they're kind of the same. It's kind of just uniform coming down, right? So I would say on my conditional distribution of my variables, my residuals are not normally distributed. They're maybe identically and independently distributed, but they're not normal, right? I've got positive skew to the distribution of these, right? This is the midline, but I've got some problems here, right? So this is something that I would want to make a note of and thinking about if I have skewed if the distribution of my residuals is skewed, what is that doing? What is that doing to my output? In this case, it's probably going to suppress your standard errors, which is probably not good. I mean, it's nice for p-values, but it's not good for sort of strong inference. So, we've got some concerns with that, okay? But if we go through, and I guess we'll switch back over this. On my marginal distribution of my residuals, do I have problems there? Not really. I mean, I got kind of a weird kind of bump here. What's going on with this bump here at the end? What does that represent? Now you're moving your arms around. What do I?
I'm trying to think of what it is.
Don't know.
I-
Breathe.
Breathe. What's going on with these residuals? So I mean, they're not sort of terribly skewed around, but they've got kind of a funky feature going on down there. What's happening with that? I'm wondering if maybe sort of this nice normal piece of things is a prediction for everybody who had a score of 0. And now this little itty bitty distribution is everybody who didn't have a score of 0. What I've got sort of 2 different things, right? And this is why we have an ordinal regression model where we've got a prediction of 0, yes, no, and then a prediction of continuous outcome out there, right? So just looking at it doesn't look bad, but it's a function of us using the wrong model and doing some stuff. I've actually got 2 distributions. I've got 2 different populations here. I've got a population of zeros and then a population of people who did not score 0, but they're just a little kind of tiny group of folks there at the end because we didn't have many people who did not score 0 at all, okay? Here, linearity is not, or excuse me, normality is not looking terrible. We got a little bit of a deviation, right? But again, what we've got here is concerns about, in my marginal distributions, it's looking fine. If I go back through and look at my conditional distribution across levels of my predicted value, I've got non-normality. I'm not getting that nice sort of even sort of uniform scatter plot that I would want. And it's a direct function of the outcome that I'm using. All right. So we've gone through, taking a look at the distribution of my residuals here. Okay. What I'm going to do now is I'm going to go through. And I'm going to go back to analyze. I'm going to go to descriptives. There's one I want to do now. So we've gone through in sort of our flow of our screening. We've got sort of everything we did before, looked at our bivariate plots, looked at the distribution of our residuals. Now I want to sort of start looking at discrepancy leverages and influence points. Okay. So I'm going to go down through. And in my descriptives, I'm just going to go and I'm going to request my studentized deleted residuals. I'm just going to ask for, I don't need Z values for that because they have already Z values. I don't need skew and curve. Or yeah, I do. Yeah. Don't worry about scanning those. And I'm going to hit OK. That's tiny to see, so I'll just switch back over to the handout. All right. So if I go through and I graph I request my studentized residuals. Okay. Here are my descriptives for my studentized residuals, and here's just my my box plot, my box plot, my histogram here. What we're really looking for here, remember, is large residuals. Okay, because we're past distributions. We're now looking at, all right, for discrepancy values, do I have evidence for large studentized deleted residuals? Those cases where my model is just way off base relative to sort of what it should be predicting. And I guess looking at sort of sort of values here, do I have problems with large discrepancies in this case? Anything else?
Z scores, right?
What's that?
These are like Z scores.
These are like Z scores, yeah. Nothing too big, right? I mean, again, rule of thumb, somewhere between values of 2 to 4, but again, we're just using these the same as we would interpret normative scores, right? Yeah, that's not perfect. We got some high values, but in the grand scheme of things, there's nothing here that would suggest a discrepancy that would cause me to sort of say, hey, what's going on with that, right? And remember, discrepancy, this is just the difference between, at least with these residuals, my observed value versus what the predicted value of that case would be in a model where that case isn't in there, right? To again, sort of avoid some of that masking stuff. So in terms of Y space, despite all the weirdness that we had with that residual plot, our discrepancies aren't that bad. So we're feeling okay with this. Then if I do the same thing with my leverages, okay? Remember that leverages are going to be weirdness in my X space. And here SPSS is working with standardized residuals. My mean value is gonna be 3P over N, which is gonna be 3 times, I've got 3 predictors over 201 is gonna give me a value of 0.045, okay? So what I'm looking at is some value that's going to sort of be exceeding that 0.045 level, okay? Now, if I go through and I take a look at my minimum and my maximum here, I do have some values that are starting to sort of fall above that, and I go, okay. I'm going through and taking a look, I've got a whole bunch of stuff going on here, but I'm probably gonna be more focused on some of these. These are gonna be my big values that are going through, and these are my largest leverage values. These are gonna be my multivariate outliers, my stuff that where there's weird stuff going on in X space. It's a weird combination of things. Okay, and so again, as I'm looking at this plot, it's looking at like case 310, 221, and 202 are probably these ones right here that are really kind of hanging out off the end of the off the end of the scale. And if I go to back to my data set, right, and I just go through and I sort my leverages. I see I've got, how many do I have? I've got 045. So I've got five values, 5 cases that are where I've got a leverage value that exceeds my threshold. But if I'm looking at this, I've got really maybe 3 that are starting to sort of kind of sitting outside of that sort of continuous distribution of everything else. I got 310, 221, 202. I could maybe throw 130 in there if I wanted to, right? 130 is just hanging out here, just right at the end of that continuous distribution. But what I'm going to do is I'm going to flag primarily 310, 221, and 202. What's that?
Throw them away.
Yeah, we don't want to do that. We want to sort of take a look and sort of scope these folks out and see what they're about, okay? So what we can do then is I told you that we can use SPSS to start to see through and hijack regression, kind of see what's happening with stuff, right? What I'm going to do is I am going to set up a command where I'm going to go through and I'm going to say compute MB0. I'll just copy this out. I'm going to compute 3 new variables, MB1, MB2, and MB3. I'm just going to create 3 new variables that are all going to be equal to 0. Okay. And so if I pull up my data set, I've got MB1, MB2, MB3, just a straight column of zeros. Okay. But if I go through and I sort my leverage values, and I go down here, what I'm going to do is for my first case, 310, that has my highest leverage value, I'm going to set MB1 equal to 1 for that case. And for MB2, I'm going to set my second highest leverage value to 1 and the third, right? So what I've got here is I have a variable, an indicator variable where a 1 indicates each one of these individual cases. Everybody else gets a 0 score, but my highest leverage value gets a case of value of 1 for MB1. Second highest leverage value gets a value of 1 for MB2. Third highest leverage, 1 for MB3.
I was just gonna ask what like MV is supposed to stand
Oh,
for.
multivariate,
Oh,
no,
okay.
you can name it whatever you want, cats, dogs,
Okay.
chickens, whatever you want, Utah, who knows? Possibilities are endless. Okay, so now what we're gonna do is I'm gonna go through, and if I go back to analyze. And I go to regression. Linear regression here. And what I'm gonna do. Is I'm gonna create a regression model where instead of predicting my outcome. I'm gonna predict MV1 based on the 3 variables in my model, okay? I'm gonna go through and I'm gonna go to statistics. I don't need any of this. Okay. And plots. Need plots or anything like that. Actually here, just hit reset. So MV1, and then we've got opiate use, pain severity, PTSD score. Paste that. Okay. So I've got a model that's just predicting MV1. I'm going to copy that. And then I'm going to use that to predict MV2 and also MV3. Okay. Just going to go through and run all 3 of these. It's going to give me the sort of models for each one of these. I'll go back to the sheet just to kind of simplify things. What we're doing here is going through and taking my set of predictors and seeing of my set of predictors, what variables are best predicting sort of this indicator 0, 1 for my outcome. Okay, is this a reasonable regression model? Is it a proper use of regression model? No, but it's kind of a hack that Tabashik and Vidal provide for identifying. I've got a case that's weird. What are the variables that are causing this case to be weird? Okay, so if I go through and I take a look for MV1, right? This is my highest leverage value. I go through and I take a look. It looks like pain severity is really kind of the biggest driver. Maybe a little bit of PTSD, right? But mostly it's a low value for pain is contributing to this outcome, right? If I go through and I look at my model for MV2, I got a high PTSD score that's driving this, okay? MV3, I go down through, I've got a low pain severity score that's driving that, okay? So in this case, so I've got 3 cases that I've identified as my largest multivariate outliers, but it looks like they're really mostly driven by sort of high scores on individual variables, with the exception of this section of this first one, there's some PTSD stuff going in there, right? So if I go through and I say, this looks like low pain and plus maybe PTSD. This one is high PTSD. And this one is low pain. Okay. And if I go through and I take a look now back to my data set, right? And I go look at these cases, okay? So 301. Again, if we look back through and take a look at when we went through and got our original descriptives for the whole set. So this person was flagged, I guess, at least in this regression model, as being weird for having a low level of pain with maybe a high level of PTSD, okay? Well, mean value of pain for the full set is going to be 4. And this has a value of 0.33. So this is someone with kind of inordinately low pain. And then if I go through and I take a look at the mean value of PTSD is 50. So this is someone who's kind of above. So I've got a combination of someone with extraordinary low levels of reported pain, but above average levels of PTSD, which really doesn't make sense in this case or in this set, given that what we generally see is as people with really low levels of pain will probably have lower levels of PTSD. So we got kind of a weird thing going on, which is probably why this case is coming up, right? If I go and take a look at my second case, 221, this was a sort of function of high PTSD. Again, my average value is 50, and this is 111. This is someone who's just like at the top of the mark, right? They're causing this to be, this is a weird value in X space just because it's so extreme on one of these variables, okay? And then the last one, again, was low pain. We have a pain score of 0, right? Which we have combined with a very low level of PTSD, which is sort of reasonable, right? And so we've just got a case that's kind of strange just because this person is looking like they're quite a bit less severe than everybody, right? Mostly due to pain, low levels of pain. And so what we want to do is go through and say, all right, these are the variables that we've identified as high leverage values. These are the specific predictors that are driving that. And this is kind of why it's sort of why these cases are weird. Now, can I expect someone to have really low levels of pain and high levels of PTSD? Sure. Can I expect someone to have just extraordinary high levels of PTSD? Probably. Can I expect someone to be sort of in this sample to catch someone who's just kind of pretty well functioning well? Yeah. So I'm not thinking about these cases as weird. They're sort of strange for the group of people that we've captured, but phenomenologically with the stuff that we're looking at, they're not. I wouldn't say that these aren't people who we want to generalize to. So again, wanting to think about like, okay, put these up, think about these things, but not get too drastic yet. Okay. So discrepancies, problems in Y space, things are looking good. Leverages, problems in X space, we've got maybe 3 cases that are looking right. And if these are the most extreme cases we've got, I'm glad I didn't go through and sort through together the whole 5 or whatever we got there. So just kind of looking and seeing what's going on with this. They're not looking too bad. So again, I'm reserving judgment for right now in terms of whether or not I need to do anything with these. Okay. Last thing I'm going to do is go through and do the same thing for my influence. Right here, I'm just going to focus on Cooks. Okay. And that's what you do. You don't need to fool around with covariance ratios. Just sort of go through, take a look at Cooks. Again, with Cooks, our threshold for Cooks is going to be 4 over n minus p minus 1, which gives us 4 over 201 minus 3 minus 1, which is going to give us a value of 0.20 in terms of what we're flagging with this. Okay. Here, seeing that we do have a max of 0.05, right? So we've got some cases that are serving as high leverage or as high influence values here. If I go back to my set and sort by my leverages, my threshold is 0.020.
Sort by your Cook.
Oh, whoops. Yeah, sorry about that. Thank you. Oh boy, there should be that many. 0.020. Yeah. Okay. So I've got that number of cases, right? Which is quite a bit. So what I want to do is utilize my graphical representations. You know, it looks like I got maybe a collection of folks out here, 130, 402, 85, 16. But here it starts to get hard. I might sort of look at and maybe focus on stuff above 0.04, which is going to give me about 5 values here, right? Wanted to go through and say, hey, these are the cases I might want to sort of keep an eye on and flag in terms of seeing if the same stuff comes up again and again and again. So last thing we wanna do is just go through and play around with one of those combination plots to see if we can get some, or see if there's anything looking strange. If we start to combine some of these things. So I'm gonna go to graphs, I'm gonna chart builder. Reset, ask for scatter, okay? And what I'm gonna put on the bottom, my centered leverages on my x-axis. And then I'm gonna ask for my studentized residuals on my y. Okay. Okay, so what I'm looking for are cases that are gonna be way up here and way down here. Is there anything that's looking too terribly bad with this? Not anything too bad. I mean, if maybe the most extreme, these folks are kind of out there in terms of centered leverages, but the residuals aren't that high. Maybe this case is really kind of the worst of what I can get, right? If I go through and I double click this, and I go to elements, I hit show data labels. That's when it'll blow up and just toss those all over the place, right? So this is case, at least in my set, the way I have it set up right now, case 201. And so if I go back to my data, okay, this is case 130, right? So I can go through and see that there, right? So once you do that, it kind of turns that plot into a mess. You can't really see a ton of stuff, but maybe that is starting to be kind of the, at least in terms of this plot, this case is being the one that's maybe kind of most problematic. But again, when you're seeing stuff that's really bad in this goes out and this is hanging out right here, sort of way far out, right? So again, one of those things that I might go through and flag, but say, okay, here are some cases that I'm keeping an eye on. Okay. All right. Questions about how we set that plot up and should we use that to, again, check through things. So what I'm going to do now, so we've gone through and say, okay, I've got a list of cases that I've flagged for discrepancies, leverages, influence points, things that have come up on my combination plot, sort of wanting to decide, are these cases problematic? Why are they coming up? What am I going to go through and do with these? Okay, so we're going to go through, last piece of things is take a look at our collinearity stuff. Anytime I'm running a regression, always nice to go through and just look at my bivariate correlations between my variables. So I've got, go through, get correlations for pain, opiate use, PTSD, and the natural log of my role function. Gonna go through, take a look at that. Any big concerns with collinearity, Olivia, in this set of data? Not really. I should have opiate use in there. I forgot to put that in there, but that needs to go in there. But nothing sort of really big. We've got some strong correlations between pain and role functioning, which makes sense. If my pain goes up, my role functioning goes down. That's a really strong correlation, right? But can I have collinearity with my dependent variable? No, it's just looking at predictor space with this, right? So nothing really going on sort of in terms of my bivariate association that's going to cause me concern. The other thing I can do then is go back up in my output, way back up to the beginning when I ran my original regression model to start with, okay? And look at here, I've got my collinearity diagnostics here on the end, okay? Again, we're looking at tolerance values less than 1.1, VIF values greater than 10, anything looking like it's problematic from that standpoint based on my tolerance, my BIF, anything there. Okay. So no issues, nothing to talk about in terms of what co-linearity is. Okay. So who's feeling overwhelmed like that was a whole lot to keep track of? Okay, that makes 100% sense. As you're going through and doing this, take good notes, put together whatever sort of structure. This is the thing, at one point, like, I'm not picking on Kate, but I remember at one point, Kate, you had asked back, oh, hey, can you, like, after the midterm, whatever, like, hey, this formula sheet is really nice, could you give us formula sheet? I could, but it's also better for you, like, in sort of in terms of just like solidifying that, like putting together a structure as I'm doing this, these are the steps that I go through, walk through and think about, kind of building that own thing that for you is really gonna sort of make the most sense to make sure I'm going through and checking my boxes. You're gonna do a lot of these, actually do a couple, sort of 3, 4 of these. This is gonna start to become pretty automatic. It's gonna get pretty quick. And it's gonna be a good way to go through and take a look and start saying, once you get some mileage under your belt, saying like, oh, this is weird, or this is not weird, or this is fine, things along those lines, okay? And this is where starting to put things together in a very structured screening report is gonna be really, really helpful for you, okay? The first part of this, easy peasy, you've been doing this before. Accuracy, plausibility, no problems. Missing values, we're good. Univariate distributions, you're fine here, right? We say skew kurtosis is acceptable for pain and PTSD. Histogram for pain indicates some negative skew. Histogram, PTSD. We're talking about histograms, talking box plots. Nothing to see here, just kind of giving a general description. We're good to go. Then we go through, we say roll function indicates clear violation of normality, right? Histogram reviews the roll function is actually an ordinal variable, taking discrete values of 0, 25, 50, 75, and 100, right? We're saying, hey, sure, here's the sort of distribution, but like the problem is it's a level of measurement issue. It's more so than sort of the distribution, right? Saying the majority of cases, go through and take a look, reporting the zero, everything else kind of falling in the scale. Box plots indicate 0 is the median, first and third quartile for the entire distribution. Like, again, this is you taking on the stat consultant role and telling your client, like, hey, this is what's going on with this stuff, right? So we say we went through natural log, broad skew and kurtosis values within acceptable levels. Histogram for natural log of roll, still non-normal, but there's only so much we can do because it's an ordinal scale, right? You've only got 5 values. We'll only have 5 values. Transform doesn't magically create new values. It's just the 5 that we've got. Okay. So we say, all right, then opioid use is balanced, half the sample reporting medication use. Always remember don't forget your categorical variables because we can't have uneven splits to the point where we will qualify those as outliers. Yeah.
I'm just wondering, like, when we determine that it's like ordinal versus continuous, like, let's say it was like it was like kind of distributed in like 5s, like so 5, 10, like all the way up to 100, like would that still be considered ordinal?
It starts to become like, what can we treat as continuous, right? Because again, true continuous variable can take on any value so within the natural range of the scale. So almost everything we're working with is ordinal, right? The question is are there enough values? Is there enough incrementation in there that we can reasonably use it as continuous? Even a 5-point ordinal scale we'll often use as continuous, right? It's just with this distribution is so whack that it really caused problems. If roll functioning had a nice sort of a more symmetrical distribution, it would be fine. It wouldn't even come up, right? But here, just the combination of the level of measurement and the way those scores fall out, it just makes this a forfeit for what we're trying to do.
Okay, that makes sense.
Yeah,
That was just my question. It's the fact that the distribution is all wonky and
Yep.
the like. The other words we're putting in there. You get what I'm saying? Okay.
Yeah. And so, but sort of given different circumstance, a different shape of those data, we could have a completely different conclusion, right?
Okay.
So this is why it takes so much sort of understanding what we're actually doing, the context to kind of pull this together to say, here's the issue, here's how we might address it.
So I guess to build off that, so like if there was like the groups by 5s, like we had 20 groups or whatever, essentially, or 20 like categories, but it had that same distribution where there was like that pretty extreme like floor effect, would we still probably consider it ordinal?
Not necessarily, because the issue there is more a function of the the distribution as opposed to the level of measurement. And if I've got something that's got, let's say, 20 different values, they're technically ordinal, right? Even if it's 10, right? I've got, or 11, say 0, 10, 20, 30, 40, 50, 60, something, that's an ordinal scale, right? But with that many values, and if we've got reasonable representation, Transform's gonna make that look a little bit better probably than just with the 5 values that we're working. So it's really our level of measurement is, but it's deceptive, right? Because you say, oh, it's a 0 to 100 scale. Well, it's not really, well, I mean, it is, but that's not what's being captured, right? So wanting to think about what's the construct we're trying to measure? How is it being represented in the data that we have? And what are the impacts on our analyses? Okay. So go down through, univariate outliers that we have to sort of have any sort of concerns about. Bivariate associations, everything's looking linear and homoscedastic. Residual distribution. Residual distributions appear normal based on the MPP and histograms with maybe some slight positive skew, but they're residual by fitted values. That was our first graph. No obvious non-linearities, despite that odd Loess estimator that we had. But we're saying this plot fails to demonstrate strong evidence of heteroscedasticity within the residuals. What we should have in there is we've also got a problem with normality, right? Acknowledging that we've got an ordinal dependent variable that's screwing with stuff, but we've got problems with the normality of the distribution. Marginally, it's fine. Conditionally, it's problematic. We're not getting that expected normal distribution of residuals. Okay. Here. Now we're getting down into our discrepancies, leverages, and influence. Got no studentized residuals exceeding 2.39. Histograms, box plots failed to provide strong evidence of problematic cases with respect to predicted values of our outcome. So we're doing okay there. Okay. Leverage values, saying 5 cases identified as leverage with leverages exceeding 3 times the expected average. 3 cases selected for continued evaluation. Here we're just talking about what we saw and what we found in those. Notice that I'm sort of saying case 310 characterized by a low pain value and then giving actual the value that we saw there. That's helping my client say within this context, this is what a low pain value means, right? With potentially high PTSD, severe PTSD, low levels of pain, right? We're saying while several of these exceed benchmarks for additional inquiry, these individuals with the 3 highest characterized by extreme scores on a single variable. So we're going to say, going to hang on to these, we're going to watch for. So what's going on moving forward. Getting down to our influence, here we're saying Cook's D for several cases, 14 exceeded benchmarks for potential inquiry. You don't need to give me all 14 of those. If we get to that point, just beg. And we got a grip of them here. Histograms for box plots identified 330, 116, 185, 402, and 130 as most influential. So again, I guess for this one, I sort of captured kind of that tail end and just saying, like, hey, here's the case, here's what the actual value is in terms of things coming up. Yeah, Kate.
You say retain but monitor for continued issues. Do you mean like we're gonna make sure that same case number doesn't come up in the influence category essentially?
Yeah, and kind of looking at some of that stuff. Yeah.
Okay.
So we're just kind of we're just laying out our case, right? And if the same people come up again and again and again and again, that's when we're going to say, maybe we take a look at this, run the model without these cases happening. Multicollinearity. The other thing too that we don't have in here, I would put something in about that combination plot to say, 310 kind of come up and had demonstrating a combination of somewhat high leverage combined with a low residual value and something along those lines, right? Multicollinearity stuff is looking good. Okay. So then we get down into our recommendations saying acceptable distributions, row functioning found to be ordinal with scores taken from only 5 discrete values. Natural log transform made things a little bit better, but still have concerns with levels of measurement. Okay. Residual plots, possible positive skew in this distribution, not severe. Sort of checking this off to sort of our outcome variable. Number of cases identified for further investigation based on metrics of discrepancy, leverage, and influence, but no major concerns were really noted, right? We've got some overlap in terms of our what we got 310, 221, and 202. Yeah, really the cases we identified as high leverages didn't come up didn't actually come up as stuff being flagged for our influence values, right? So we're saying despite reasonable adherence to statistical assumptions, measurement of role function is a discrete ordinal variable continues to be problematic. Basically, what we're recommending is probably need to go through and use a different model that's developed to account for our actual outcome that we're using. Right. So again, that was a whole lot of stuff to say, you know, and you can think about like if we actually had a well-performing and a good outcome variable, a lot of this stuff goes away, right? So we don't have to worry about it. But it's just kind of going through and saying, hey, cards on the table. This is kind of what we got going on. This is what you can do, strengths and weaknesses. Yeah, we can probably go through and proceed with a regression model without, I mean, it's probably interpretable, right? It's not the best model that we could run. If I was going to publish this, it's not the model I would use, right? But it'll probably service, right? If you're running a thesis or something like that, you are not interested in learning about ordinal regression. Just because that's not on your list of things to do, you can probably get by. But what I would want you to, and hassle you with this, but what I would say is you would want to be able to talk about like, hey, this is the model I chose. And these are the things that are maybe kind of wrong with it, or these are the nuances of the data. Understanding that this is what's going on, here's the caveats to sort of the interpretations that we're making. Yeah.
I need you to explain to me one more time. To the point of, I got very lost at when you were computing the new variables, the
Yeah.
multivariate. Why?
The new what?
Why?
MB1.
Yeah, like MB1, like why did you?
It's just a placeholder. Don't worry about the names. That's just a placeholder because what I'm gonna do is I'm gonna regress that case onto all of my predictors. And what I'm looking at is to say, what variables predict the presence of that case? Okay.
So basically it tells you like which one of the variables is like making it weird, like why is it an outlier? So like the ones that were significant or like close to significant were like the ones that were like really contributing it to be like further out there, like not a normal case.
I think like where you got lost was maybe, well, how did you sort them before assigning the one?
Oh, I sorted it by leverage value.
Leverage?
Yeah.
I think you just, I don't know how yours was sorted before, but I think that might be.
Sort of.
Okay.
So yeah, you just got those from the smallest leverage to the highest value, and those three variables, those are just indicator variables, just to flag those individual cases. So that one value is just a mark, hey, this is this case. And it's not a proper regression model in that you can like sort of infer anything from it because you're using our ordinal regression on a dichotomous outcome. So but for the purposes of just saying like, here are the variables that are contributing to this case being this case, that's what's going on with that stuff. Yeah.
So if you had like 5 that were like exceeding your benchmark, would you do like MB1, 2, 3, 4, 5?
Yeah, probably.
Okay.
Yeah. And it's kind of a like, how far do you go, right? Like you can go, it can be a Sisyphean task where you're just sort of consistently trying to roll that boulder up the hill. And if we do go through, this is the important thing. If you go through and you find cases, you're like, nope, this is way problematic, right? We need to get rid of this case. What you then need to do is get rid of the case and then go back and redo it again. Because what happens is sometimes if you get rid of that case that's problematic, what that case can do is mask other cases that didn't come up before. But now that you've got that person out, now we had a couple of other things kind of pop up. At some point, you have to think about like sort of what's reasonable here. If I was just like hard line, like, no, this is the cut point. If it's over 0.02, then it's absolutely terrible. And I got to kick, then I'm going to lose most of my, just going to narrow this. I'm going to whittle it down until I got 50 cases. And then I'm not going to be able to run my model because they're all going to be people who scored 0 on my outcome. So then I've got a constant, right? So you got to be thinking about like, what am I doing? How far do I need to go? this is maybe not great, but it's tolerable. Basically life lesson, like I'm not super thrilled about this, but I can deal with it, right? What we're really looking for are things that like way off base, stuff that's gonna be people who aren't taking our study seriously, wild miscodes in our data, people who are just categorically different than sort of who we're trying to go through and take a look at, or maybe a subset of cases that just our model doesn't do a good job accounting for, right? I've got a collection of cases, and if I go through, and this is why we don't just throw people out, always got to go through and say, what's going on with these cases? What I find, I might have a subpopulation that sort of, hey, my model works great for most people, but for these folks, it really doesn't. So what's going on with that group of cases? Why does it not apply? Is this a research question? Is this something that I can sort of go through, pursue? What does this tell me about how we understand this phenomenon? There's a lot of information to be had and a lot of cool information to be had from this. So it's strongly, if you approach this in anything as just a rote task to do and keep track of, it's going to be miserable. It's like pulling toenails, okay? But if you think about like, so what are we trying to do? If we're trying to understand something about phenomena and sort of think about like how things fit together, it's always going to be a little tedious. It becomes less tedious if we're trying to think about it as a conceptual level, as opposed to like, what are the steps that I need to do to not fail the class? Okay. And it's easier to do with your own data that you're interested in, as opposed to my data that you have no reason to be interested in, but sort of just try and take that approach. All right, cool. Let's spend a few moments just talking about some variations on multiple regression. All right. Standard multiple, simultaneous or standard multiple regression. This is what we've been working on in class. Okay. Here what we've got is all of our predictors are entered into a model simultaneously. Okay. And in this, our model is looking at the unique association of our individual predictors with our outcome. Okay. Controlling for everything else, covariating out. It's just looking at the unique association of this with my outcome within the context of the model that I've created, okay? And so again, as we talked about, because our predictors are correlated, it's very possible to have a given predictor have a small unique association with my outcome, despite its large bivariate association. Probably what that means is that my predictor is highly correlated with other predictors, and that highly correlated predictor also predicts the same portion of variability in my outcome. So we just got overlapping things. Everybody brought corn chips to the party, and so now no one's super excited about corn chips. No one gets credit for corn chips if everybody brought the corn chips, right? And so then everybody's like, oh, we had a party, but we got lots of food, but no one's super excited. Okay. So important to look at both bivariate correlations as well as our regression coefficients. This is going to be a nice way also to ferret out stuff like suppression effects. If I've got a strong positive correlation with my outcome, but in the context of my regression, I've got a modest negative correlation with association with anything, it sounds like something's gone through and flipped around, right? Tabachnik and Fidel talk about suppression effects really poorly. Has anybody sort of read the belly dancing example that they give? Okay, it's really bad. Okay, make sure that you're going through and reading that chapter. That's bad example. They're just really into it, and it's made it its way across multiple editions of the text. I don't get it, but they seem to like it. But they're both, they get to make decisions. Okay, so again, with our simultaneous regression, looking at the unique contribution of individual predictors while accounting for other variables in our model. Okay. Now we talked about our unstandardized coefficients interpreted as based on this model, the expected change in y given a unit change in x, right? Our standardized coefficients given a unit expected standard deviation change in y given a standard deviation unit change in x. This is our standardized coefficients are a nice way to go through and compare across predictors in our model, which ones are relative strength. What's not appropriate though, is to go through and compare standardized coefficient for variable A in this model against standardized coefficient for variable A in a separate model with a separate set. What happens is we compute those standardized coefficients by changing everything to z-scores, right? And if I have samples that don't have similar variances, that goes through and changes the scaling. And so now we're comparing two metrics on a non-common scale. Okay, so when we're using standardized coefficients, the best thing to do if I want to compare predictors within a model, standardized coefficients are the way to go. Go through and just take a look. It puts everything on a common metric. But if I've got a coefficient in this paper and a coefficient in this paper, standardized coefficients aren't the way to go. Go back through and look at your unstandardized coefficients across samples. Because what happens is if I happen to catch a sample that has much greater or smaller variability in this group than that group, that's going to throw my standardized coefficients off. They're not going to be the same, working on the same metric, even though they look like they are. Okay. All right. So we went through, and this was our example. We went through, looked at, does PTSD, pain severity, and opiate use count for meaningful variability in role functioning among accident survivors, right? What's this question asking about? What statistic do we get that addresses sort of part one? This is my R squared, right? This is the combination of these together. Does it predict variability in my outcome? Okay. Then number two, what's the unique relation of PTSD, pain, and opiate use with role functioning? This is where I'm looking at my individual coefficients. Together, does the best linear combination of these predictors predict variability in my outcome? Look at my R squared. If my R squared is different than zero, it says, yeah, at least some, right? This one, second one, looking at unique predictions in my individual variables here. So we go through and take a look at sort of my outcome. Here, I've got my R squared of 0.38, suggests telling me that the best linear combination of opiate use, pain severity scores, and PTSD is accounting for about 38% of the total variability in the natural log of role functioning. Here is, if I want to see if whether or not that I have evidence of that being some value that's different than zero, I go down to my ANOVA table, take a look at that. I've got a very small p-value, I've got a massive F value, so it's telling me that yes, I have evidence against the null hypotheses that R squared value is equal to zero for this model. Down here, I have my individual coefficients. I have my constant, right? This is telling me my expected value of the natural log of role functioning if everything else in the model is equal to zero. So if I have someone, and this is really, really, really important, think about what this literally means. If I have someone who is not using opiates, who has a score of zero on pain, has a zero on PTSD, what would I expect their natural log of role functioning score to be? I would expect it to be at 4.33, okay? Now, this is where the natural log of role functioning doesn't mean anything, right? Like, I don't understand what that means necessarily, but this is what I would expect that to be, okay? Now, if I go through and I take a look at my individual predictors, right? Opiate use, p-value 0.84, opiate use isn't doing much, okay? Within the context of this model, knowing whether or not people are using opiates or not tells me no meaningful information above and beyond knowing what their pain score is and what their PTSD value is, okay? Now, if I go through and I look at my bivariate association, though, if I look at opiate use with the natural log of role functioning, I have a small correlation there, right? That's not zero. I've got a correlation of negative 2, 3, right? And again, opiate use coding 0, nothing, 1, yes, suggesting that as opiate use increases, functioning decreases. There's a small association there, right? So in the bivariate case, I do have a relation between these two variables, but as soon as I go through and account for common variability with PTSD and pain severity, now all of a sudden it's not contributing. Like, it doesn't add anything to my model, okay? So again, thinking about this bivariate association relative to my partial coefficients down here controlling for, accounting for, after we pull out shared variability, covariant for, however you want to say that. What we're saying is, yeah, in the bivariate case, association, but once we come to the party, not bringing anything new, and so nothing really kind of coming up with this. Okay. Now, if I go down through and I take a look at pain severity on the other hand, very small p-value. T statistic is huge. I look at my unstandardized coefficient here, a value of negative 0.69, saying that for every unit increase in pain that I'm seeing, I'm expecting corresponding 0.69 unit decrease in the natural log of roll functioning. Again, problematic because I don't know what the natural log of roll functioning means, but we'll get to sort of some ways to go through and help out with that. Okay. If I go through and I take a look at my standardized coefficient here, negative 0.57, let's call it. Okay. Here, saying that for every standard deviation unit increase in pain severity I would get, I should expect a little over a half a standard deviation decrease in the natural log of roll functioning. Okay. Is this a reasonable size effect? Yeah, I mean, that's a decent, if we think about this kind of, our standardized coefficients aren't bounded by negative 1 to 1, but they're they are generally about that, right? And so we've got a pretty strong effect going on here, right? I drop down to my PTSD total scores. Here I've got a really, really small value, negative 0.013, right? And if I just look at that, does that seem important or big? Doesn't seem like it at all, right? But remember that PTSD scale ranges from 0 to 120 or something like that. What does a 1 unit increase in PTSD mean? Not much, right? Versus our pain scale goes from like 0 to 6. What's a 1 unit increase in that? That's a huge jump, right? And so even though this seems minuscule, right? I'm still getting strong evidence that it's not 0. If I go through and I take a look at my standardized coefficient, it's not large, but it's not 0, right? So if I'm looking at this, I'm seeing that PTSD or pain severity is definitely the big driver. It's the thing that's accounting for the most variability in roll functioning within this model. But PTSD is contributing something above and beyond pain. Like even once we account for pain severity and opiate use, PTSD scores driving a little bit of a continued reduction. Here, for every standard deviation increase in PTSD score, we're getting about a 1.6 or 0.16 standard deviation reduction in the natural log of roll functioning. We've got a respectable p-value here, right? Lower and upper bounds, confidence bounds for my unstandardized coefficients. And then here at the end, this is where we've got our effect sizes, okay? Here we've got our bivariate, our 0 order bivariate correlations. Okay, that's the same thing that we're getting up here. Okay. Partial correlations. This is going to be our partial coefficients. This is if we go through and square these, we can interpret these, remember, as reflecting the proportion of residual variability in the natural log of roll functioning attributable to a predictor after we pull out to a variability that's attributable to other stuff in the model. Right. So here's the total piece of the pie. If I take what we can attribute to opiate use and PTSD, pull that out, right? If I were to square this partial correlation, that would tell me of whatever's left over, this is how much we can chalk up and say is attributable common with PTSD or pain severity, if we're talking about that. Same thing here. If we pull out variability attributable to opiate use and pain severity, take that out of the model, which is a much bigger piece, right? Of what's left over, this is what of what's left over. If we square this, this is what's shared with PTSD. Okay, so remember that this is a proportion of residual variability attributable to a predictor after we pull out everything else. Here, this is our semi-partial correlation. Okay, this is easier and nicer to interpret because it says within this model, if I go through and I square this, this is saying whatever that value is, say like 5%, say 5% of the total variability in the natural log PTSD is unique to this variable, right? So we're just getting the piece that's unique, but it's the total piece of the pie. The denominator changes. Here, the denominator jumps all over the place. Here, the denominator is always 100%. Of all the variability in my outcome, this is what's uniquely attributable to this predictor once we account for other variables in the model. Questions about interpretation. What I want you to be able to do is interpret sort of, and so I can point to anything in this output. You can tell me this is what it is, this is what it means, this is how we would go through and interpret it. Okay. Questions on that? All right, and this is what it looks like it's stated. Okay. We'll stop there. Question for you all. Some decision points to make in terms of what we want to do. So we've got a handful of slides left to just kind of talk about mostly the difference between what's going on with the hierarchical regression model and sort of our standard regression models. It's not much. Won't take that. I mean, the thing is, like, people think that hierarchical regression models are magical. They're not. They don't give you anything above and beyond a change of R squared. Like, that's the end of it. Okay. We could have our next set due on Friday as scheduled in the syllabus. Okay, that would keep us on track with stuff. We could also say, well, we're not through this. We still have some slides to do. Let's wait until we go through and get through those slides and then sort of assign the problem set. We could do that. The problem is what that's going to do is that's going to put your regression set for this one, which is going to be new and kind of big because it's new stuff. And it's going to put it closer to that moderation set. It's going to be kind of a beast to run through. It's always easy to kick things down the cans down the road. But in terms of spacing out and thinking about your workload, probably giving you a little bit more breathing room between these is probably going to be better than not. So the question would be, do we sort of keep our regression set that you've had out for a while and sort of kind of looked at it and sort of hopefully start poking around with it, do at the end of next week as in the syllabus and stay on track with stuff? Or do we wait and say, nope, I'm fine with that being sort of stacked up against the moderation set. Let's push it back a week. I personally do not care. What I just won't want to do is if we do that, then have people sad and upset and tell me they're stressed out because we've had sort of back-to-back sets. So it's sort of like 1 cookie now or 5 cookies later, kind of the situation that we've got going on. Yeah.
Can we push it to like Monday instead of like Friday?
It's not due
That's an
this
idea.
Friday, it's
I
due next
know.
Friday.
Yeah.
Yeah,
She means like, yeah.
mine, you know, a compromise
A compromise.
of making it due on that, the Monday after the Friday it was supposed to be due.
My only reservation with that is that Matt has to go through and sort of work through those and think about sort of all the other things that Matt has to do. And then giving it back to me so that I can get those in time to score those, get those back to you so that you have those in hand so that you can go through and sort of use that as feedback on the moderation set that will be sort of a bigger and more involved thing.
So it's up to Matt.
My schedule, that's gonna be a nightmare, but I would try.
I don't want to,
I'm honestly fine with staying this Friday.
I don't care.
Let's do this, okay? Let's keep it sort of not sort of this Friday, but the end of next Friday, kind of where things are at. Also, so we'll finish this, we'll finish the rest of the regression stuff up in class, but also we've got video online and just covering this, and this is not a lot of what involves sort of the actual set. So like the actual things that we haven't gone through yet are only a small portion of the set that you're going to be doing. So let's do this. Let's keep the set due at the when it is on the syllabus. if you're sort of wanting to go through, get a jump start, and things like that, I'll sort of make sure the link is posted to the last of these slides, just so you can kind of see what's going on and things along those lines. But really, what we have left to cover is such a small piece of the overall set. Objectively, it probably doesn't make sense to sort of push it back just to go through and cover that stuff, but we can go through and there's maybe like a half an hour worth of stuff to go online to watch. So the last piece of this, okay.
And you're telling me that everything that we just did today was like just screening stuff, right?
Yeah.
That's right. I just want to make sure that.
And that's gonna be the biggest chunk of this, Haley. You're gonna have to do a couple of these, and you already know how to go through it and sort of go through and do that now. You've had the whole thing, so let's do that. Let's see where things are at. Jump on this, sort of get started if you haven't. And again, like I'm just trying to save you some stress and headaches of having multiple things back. I want to give you a little bit of a breather in between sets, and so that's just what we're trying to do, and to be respectful of Matt's stuff. So let's shoot for that. All right, we can be flexible if something comes up, but let's shoot for that. All right, awesome. All right, thanks everybody.
It was nice of you to give us the options.
Well, I mean, I don't.
It's 5:06. But I'll forward the email to you. I don't see. Thank you so much.
Was it the illusion of